So today we're going to use differentials to approximate a value. In this case, we're going to use differentials to approximate 31.96 to the 2/5. So I think first we probably need to discuss what differentials are. Okay? So differentials are another method, like linear approximation, for approximating values of a function. So let's draw a picture, see what we're talking about. So here I have a curve. Okay, so let's call this my curve f of x. And let's say that I know the value of the function at some point. We'll call this where x is a. And let's say I'm trying to figure out the value of the function where x is b. Okay? So, the value of f of b is going to be the value of f of b, or the y value here. Call this f of b, and then my y value here is f of a. The y value at b is going to be the y value at a plus some change in y. I'll call that delta y. So we're going to add the change in y to the y value here, and that should give us the y value at b. So for whatever reason, let's say we cannot figure out exactly what that change is. Well, here's where an approximation comes in. If I draw the tangent line at the point, here's my tangent line. If I draw the tangent line at the point a f of a, then I'm saying that the tangent line can help me approximate the y value here. How come that works? So the change in y over the change of x, if I'm close to this point where I have the tangent line, this change is going to be pretty close to this change. Okay? And if I calculate that, well, what's that? That would give me the slope of the tangent line. So this is approximately equal to the slope of the tangent line. It's close. And obviously, the closer this point is to this point, the better the approximation is going to be. So I'm going to say delta y, delta x is approximately the value of the derivative, which means that delta y is approximately the derivative times delta x, whatever my x changed by. So if I plug this in here, if I use this approximation in this equation, then I can say that f of b is approximately my y value at a plus the derivative when x is b. This means when x is a times delta x. Alrighty. So let's put this all into action and try and approximate 31.96 to the 2/5. Okay, so I need a function. What function might I use to approximate 31.96 to the 2/5? Well, I know I can figure out what 32 to the 2/5 is, so I think I'm going to say, let's let our function be x to the 2/5. And let's let our a value, or our starting value, be 32. And our b value, or the value that we're estimating, is 31.96. Okay, so I need a couple of things. I need the y value when x is 32, or I need f of a. So f of 32 is 32 to the 2/5, which is 2 to the 5th to the 2/5, which is 4, or 2 squared. And then what else do I need? I need the derivative when x is a. So the derivative when x is 4. So the derivative is 2/5 x to the negative 3/5. So the derivative at a, or when x is 32, is 2/5 32 to the negative 3/5. Well, I know that 32 to the 1/5 is 2, and 2 to the negative 3rd is 1/8. Here, I'll show that right here. This is 2 to the 5th to the negative 3/5, which is 2 to the negative 3, which is 1 over 2 cubed, which is 1/8. And so I get my derivative is 2 over 40, or 1 over 20. Okay, so I found f of a, I found the derivative when x is a, and now I need delta x. Well, delta x is my change in x values, or my b value minus my a value, which is going to be 31.96 minus 32. So our change in x is going to be negative because we have a target value less than our starting, or our a value. So this is negative 0.04, and I actually think for this calculation, since you're usually doing this without a calculator, it might be easier to write this as a fraction, and so that's going to be negative 1 over 25. Okay, we are ready to estimate f of b using our differential approximation. Okay, so the function value when x is 31.96 is approximately, so all my parts are f of a was 4 plus the derivative when x is a, which is 1/20th, times my change in x, which is negative 1/25. So 2 times 25 is 50, so this is going to be 4 minus 1 over 500, or 2,000 minus 1 over 500. I should be writing approximately here. This is an approximation, or approximately 1,999 over 500. Okay, let's see how good our approximation is. So I'm just going to check this with a calculator. So 1,999 divided by 500 is 3.998. So our estimate is 3.998. And the actual value of 31.96 to the 2/5 is, oh, that's a pretty good estimate. 3.99799. So we are good to the nearest thousandth. Very good estimate. So you might wonder why we are estimating these things when we can just find the answers using a calculator. But linear approximation, or the process of using a tangent line to approximate, is used throughout mathematics and in applications of mathematics. So it's really important to understand the reasoning behind linear approximations. Linear approximations can also be used to check computers and calculators and their speed and accuracy. All right, linear approximation using differentials.